Hello, this is Sean Mullery from Electronic Engineering at IT Sligo, and in this short video lesson I'm going to introduce you to a special library function that the Xc8 compiler has, which is the delay function. Now there are other ways, and indeed better ways, of doing a delay than this, if we want to time something well, and if we want to make sure that the processor can do other things while it's going on. But for the moment, I just want to introduce this very simple version for you, because it's one that comes with the Xc8 compiler and you can use it very quickly. We look at other types later on. So what I need to introduce to you first is the actual Xc8 User Guide. I've put that here at the top of Moodle in the Moodle subject, so you can see it there, the Xc8 User Guide, and I happen to have it open already here. It's quite a big document. Again, it's really only for you to dip in and out of every now and then if you want some information about the Xc8 compiler. I'm going to do a Control F here, and I'm going to look for delay. And we can see we've got 63 different mentions of delay. But we can see here the one that's come up first: how can I implement a delay in my code? And because the little hand symbol has come up, I can obviously jump straight to there. So it's written down here: how do I implement a delay in my code? Okay, so if an accurate delay is required, or if there are any tasks that can be performed during the delay, then using a timer to generate an interrupt is the best way to proceed. That's the other way that I mentioned to you that we will look at later on. But if these are not issues in your code, then you can use the compiler's inbuilt delay pseudo functions, which are delay, and that's an underscore delay underscore, two underscores, then with delay underscore ms, ms standing for milliseconds. And you can also have a double underscore delay underscore us, and that stands for microseconds. The Appendix A library functions is where we can take a more deep look at that. These all expand into inline assembly instructions or a nested loop of instructions, which will consume a specified number of cycles of time. Okay, so what we're going to do is we're going to look at the Appendix A. So I'm going to click on that and have a look at it here. And just click there and click on the, oh, that's brought me straight to the second one. I didn't want to do that. So just take a quick move through here to see if we can find the delay. There we have it. So delay ms and delay us are the ones that we're going to look at. And what you do is you use them in this format. You must put the two underscores before it and the underscore in the middle. And then where it says X there, you should put in the number of milliseconds of a delay that you want. Remember that 1,000 milliseconds is a second, and 10,000 would be 10 seconds. As is often more convenient to request a delay in time-based terms rather than in cycle counts, the macros delay millisecond and delay microsecond are provided. These macros simply wrap around the delay number of or delay n and convert the time-based request into instruction cycles based on the system frequency. Now that means we need to know what the system frequency is. Of course, we're working on the simulator, and the system frequency it's not meaningless there, but it certainly doesn't operate at exactly how it would operate on a chip. However, there is one important point here. In order to achieve this, these macros require the prior definition of a preprocessor symbol underscore xtal underscore freq for frequency. This symbol should be defined as the oscillator frequency in hertz used by the system. Now, what we're going to do is we're going to actually put that into the into our program to have a look at what it does. So we're going to have to define that xtal freq, and then we're going to use the delay ms. And I'm going to use some numbers that have worked for me, but they're not exact for what we want. They're not exact numbers because they're going to work on the simulator. Okay. So the first thing then that I need to do in my program is that I need to set up this hash define xtal freq, and I've set it for 250,000. Okay. Which is assuming that it's running at just about a quarter of a megahertz, which would be quite slow. Now, so make sure you write that in your own code. So it's then as a hash define. Now the next thing then is, what I'm going to do is I'm going to use a previous problem that I asked you to do, which was I asked you to put out different sequences out to the port B pins. So I think the first one was that I wanted you to put out all ones and for the first 4 and all zeros. Then we do a repetition of that. So this time I wanted 5, 5 because that was what was going to give us 0, 1, 0, 1, 0, 1 and 0, 1. And lastly we wanted the opposite of this, then 0, F. Okay. Now the problem with that on its own is that if we were to run this and we'll just look at the I/O pins here. Oh, sorry, I forgot to do something that that I set earlier on, which was that I set TRISB to TRISB has not been set to all outputs. Okay, so to remember, for all outputs, we're going to set that to 2 zeros. So we'll just run that again and debug again. And if I look at the I/O pins here, what I'm seeing here is just the digits are constantly changing and I can't really make any sense of them because what's happening is that in my main function it is changing from this to this to this, and then of course because this is in a while one, it is repeating and repeating and repeating forever. Okay, so it doesn't make much sense to me. So there's two things I can do here. Firstly, I can stop it there at one of these, and I can see that I have all zeros in the top half and all ones in the bottom half, and I can use the step function. This is the step function here to move through it one by one. We can see that it's now changed over to all ones in the top half and all ones in the, sorry, when I say the top half I mean the most significant bits, and all zeros in the least significant bits. Then we should change to 0, 1s and 0, 1s, and that's what we've done. And then we change to all zeros in the top, in the most significant bits, and all ones in the bottom, and we go back like that. But rather than me doing that, what I might like to see is I might like to see a sequence actually happening. So what I can do is I can put a delay function in here, a number of milliseconds. And I'm going to put 10,000 in there, which would be 10,000 seconds, which seems a huge amount, but I found that the simulator seems to run quite fast with the oscillator frequency that I've chosen. So just to slow it down a little bit, I've put that in. So I'm going to put one of these in after each one of these so that I can then see it happening in sequence. And so again, so you can now see it changing through them, cycling through the 3 different things that we have there. Okay, and it repeats as well. Okay, and that's because it's inside this while one. Okay, so in the next few exercises, what we're going to be looking at for you to do is to put different sequences out there, but we need to actually slow them down to a speed that you can actually see them occurring. And rather than having you stepping through in each case, we'd like to actually see it running free and you able to see the sequence that's going on.